All right, continuing the AI lecture series topic on constraint satisfaction problems. Today we are talking about the MRV and LCV heuristics. So within the constraint satisfaction problems, we've already talked about how to represent the constraint satisfaction problems, how to model them as a graph. And today we will be talking just about how to use the backtracking search algorithm with heuristics, specifically using the MRV and the LCV heuristics. We'll talk about what they are. And we will still need to talk about the constraint propagation and the graph decomposition in some of the remaining videos. So just as a quick refresher, constraint satisfaction problems are a specific subset of search problems where a state is defined by variables xi. There are many variables, and each variable has a values that it can pick from a domain D. Sometimes all the variables have the same domain. Sometimes each variable can have its own domain. The goal test is a set of constraints specifying the allowed combinations of those values for those variables. And it's a general, what we're interested in is useful general purpose algorithms than just using a simple search. So this algorithm is generally what we refer to as a backtracking search. Search just like we would do a DFS kind of search, but in this case we're given the state where each variable has an assigned value, the successor function, which means that you take an unassigned variable and assign it a value. So that's the transition that we're making. The goal test is that all the variables have values and then their values are all satisfied the constraints that are given. Because there are n variables in this backtracking search, all goal nodes are at the same distance. So therefore, using an algorithm such as A star is not really helpful because distance is just fixed. The main problem here is satisfying those constraints. There are many examples of CSPs, coloring, scheduling, etc. And again, the variables can be finite, infinite, uncountable, etc. Now the question again we're interested in is on how to improve backtracking. What's a general purpose idea that we can do to get good amount of gain in the speed just within the backtracking? Two things we really look at. One of them is ordering, which means which variable should be picked next and what value should be assigned to it. Then there are other things that you can do, which we won't talk about in this lecture, but we will talk about in other lectures, such as how can we reason with the constraints and how can we understand the structure of the CSP graph to solve it even more efficiently. There are two main heuristics. That's what we need to get to. The first main heuristic is which variable to pick. The variable ordering is given by minimum remaining values. This variable is called as just the MRV variable. So you should always choose the variable that has the fewest legal left values in its domain. A quick example is that when we are playing Sudoku, we look at a cell that we know can only be two values. We see that this particular cell, because of the other values that are already present in the same row or the same column, this particular cell can only be 2 or 9. So we will try to assign 2, and then if that works out, that's great. If not, we'll backtrack and try to assign 9. So this particular heuristic is very intuitive. We would also do the same, that we would pick the variable that has the minimum remaining values, and this is basically the MRV heuristic. It's also called the most constrained variable, and this kind of ordering can be called the fail fast ordering. So we want to pick the vertex, the variable that has only a few values. So we try one value. If it does not work out, then we know we have eliminated that. So that's very helpful because then we have eliminated one of the domain values from that variable. We are left with even lesser values there. There can be a tie-breaking rule, especially in the earlier stage, because you might have many variables that have the same number of domain values left. In that case, we can consider a variable that is involved in more constraints. Even after this rule, multiple variables may still be tried, may still be tied for the same value and same number of constraints, but at least these two give us a certain ordering here. The next main part of the heuristic is which value to choose. And here we sort of take the opposite approach. We choose the least constraining value, which rules out the fewest value in the remaining variables. It's not straightforward on how to do that. You have to try each and then see which variables are affected, which values get eliminated, do the computation, and then choose the one that takes eliminates the least number of values from the other variables. In this case, first of all, you can question why least, why not most. You can try with the MCV as well, the most constraining value. But from the empirical results, the MRV plus LCV combination often gives you at least 2 orders of magnitude improvement over not using those. For example, in backtracking search, if we don't use MRV, LCV, we can solve for about 25 queens using in the n queens problem. But using these two ideas, we can already get to 1,000 queens. If you try just to use MCV, you'll find that actually MCV performs even worse than not ordering the values at all. So you can try without doing anything, use MRV, the minimum remaining values variable, that already gives you 1 order of magnitude. You combine that with LCV, that gives you 2 orders of magnitude improvement. Again, that's coming from empirical results. And those two heuristics are sort of the mainstay of any CSP algorithm. And in a future lecture, future video will talk about forward checking, constraint propagation, and how to use the structure of the constraint graph.